This is a second in a series of 4 quick videos on strain gauge usage and how they're used in strain gauge force sensors. This video focuses on the Wheatstone bridge. We've already talked about why it's required, right? We're going to show here quickly how it relates to other types of bridges and what this gives you and what you should know about the basic Wheatstone bridge in its use. The basic idea in using a Wheatstone bridge is to basically convert the change in resistance into voltage. Here, in a more general case, is a change in impedance to voltage. You want to think back to a simple case. The simplest case that I like to think of is of a signal conditioning circuit of this type is of a simple voltage divider. So let's say you had a resistance here that you wanted to monitor its change. Let's say that is changing because it's a strain gauge. You would configure it in a voltage divider circuit, have maybe a fixed resistor here, and you put in some input voltage, and then you sense across the sensing resistor what is happening. And there's a simple relationship for a voltage divider, right? So this is one example of a signal conditioning circuit that can monitor resistive changes, converting a change in resistance, right, to now a change in voltage, which is now easy to measure with a simple data acquisition or A to D input, say on a microcontroller and so on. So impedance bridges, a little bit more general case of a signal conditioning circuit for impedance, again, is a more general term for anything that's a more complex function of resistance, capacitance, and inductance, if you like, right? It could, in general, have a complex and a real part. So impedance bridges are a more general type of signal conditioning circuit used to convert these types of sensor impedances into voltage changes. There are many types of impedance bridges. And if you have an impedance bridge where all of the bridges, and I'll show you in a second what I mean by that, it's all resistors, then that's the specific case of a Wheatstone bridge. So let me show you this table here. I kind of like is showing you many different types of impedance bridges. For example, this one has capacitors, and so they're all, don't worry so much about the detail here, just to show you that impedance, there's many different types of impedance bridges. The case where all of the arms, the arm meaning, the 4 arms, if they're all resistive, that's when you have a Wheatstone bridge. So I won't worry too much about just to show you that the general case of the impedance bridge covers the case of the specialized case of the Wheatstone bridge. The other thing to keep in mind is a balanced bridge that's simplified to the Wheatstone bridge. We say that it's balanced when the ratio of resistances of any 2 adjacent arms is equal to the ratio of resistances of the remaining 2 arms. So if you have R1 to R2 equal to R3 over R4, then let's say I put in some voltage here, some input voltage, then the output voltage here will be 0 if it's balanced, right? So imagine now these are strain gauges, and if any one of those changes, so usually in a Wheatstone bridge with strain gauges, all these would be the same, right? So if any one of these changes slightly, right, there's a little delta R, say, due to a strain of this resistive strain gauge, then this guy's, right, going to change from 0, right? It won't be equal to 0. That will be an unbalanced bridge. So that's how we basically detect now changes in resistance, through this bridge. Okay. Now, showed you in a previous video how even for a single strain gauge resistor, if I change that R a little bit, right, the delta R for a given strain, right, is very small. And even in this case, when you have changes in resistance now due to strain, if you have the delta V0, if you like, is still going to be small. It's going to be on the order of millivolts. So that's why, as we'll talk about in another video why we typically will attach this to an amplifier. So we'll talk about a bridge amplifier in another video.